All right, so what would the electron configuration be for aluminum? Al. Okay, aluminum is Al. What's the electron configuration? 1s2. Okay. 2s2. Okay. 2p. So if you 2p6 and then 4s. Three. Okay, 3s. How many? 3. 2. Oh, and then 3p1. 3p1. Okay, good. So if you use your periodic table, let's pull up a periodic table. If we use our periodic table, that can help us, the shape of our periodic table. Oh, let me find a. So I'm just gonna go 2p table. Okay, so aluminum is right here. So these two columns are our S. So if you go up here, those are S. So 1s2, or 1s1, 1s2, and then these are our 2s. These are our 2p. So there's 1, 2, 3, 4, 5, 6 there. Okay. So we can use our periodic table to help us with this. Now we're in the 3. 3, this is our S. 3s, 1, 2. And then this is our 3. This is a p block. So if we're only here, we only have 1 in the 3p. Does that make sense? Do you see that? So if you can remember, the shape of your periodic table helps you fill those shells. Okay. The other thing, have you guys used this periodic table very much? This one, if you click on electrons, it can help you fill. So let's go to aluminum. We just did aluminum. It can help you with the electron configuration. So if you want to practice, and then this also shows you. Oh, this one shows you the S block, the P block. Okay. So we will stop at argon for our class. But yeah, if you took another chemistry class, you might need to do cobalt or something. And you can stop for a further one. Use the d orbitals. Okay. All right. So do you think you could do that on the final now? Yes. You could do the electron configuration. Okay. So be practicing that in Alex. Okay, the next thing that we need to do is our lab 4. We need to talk about how to do the equations. We didn't really talk about that. So go ahead and pull out your lab 4. Okay, that's okay. All right, so we did this last time, right? And some of us finished during. Oh no, like we did the lab class. We did the test before. We did it a while ago. Okay. So here, hopefully you have your observations. You have observations here? Great. So this is observations. Hopefully you've already done that. And then what are we supposed to do here? What do these blanks mean? We need to balance this, right? So how many moles of magnesium for how many moles of oxygen gas gives us MgO? Good. 2, 1, 2. Okay, I'm going to let you do that, but that's what those are. Some of us were asking, what are those bins for? That's for balancing. What does this mean? Write in words. What does that mean?
It means like what happened. So
what happened? Okay, magnesium.
Into an oxygen-rich plane produced by magnesium monoxide.
Okay, so how do we name this one? So I really like that. You got lots of descriptive words. Let's remember how to name an inorganic compound. This one's just magnesium oxide. Good. Good. Okay. Let's remember, what's this one called?
Magnesium.
And what's this thing? So we don't use prefixes in inorganic. What was this thing? OH. It's oxygen, hydrogen, hydroxide. Good, Chloe. This one's hydroxide. So magnesium hydroxide. Good. Okay. So what would this be here? This one's copper oxide. And then copper, remember, copper is a transition metal. So we have to say the charge on it. So what's the charge on oxygen? It's a 2, right? 2 minus. So what's the charge on copper to balance that 2 minus? 2 plus. So what would the name be for this one? So don't use no prefixes in inorganic. This would be copper. And we need the Roman numeral. We need the Roman numeral. If it's a transition metal, we need the Roman numeral. Copper 2 oxide. Okay. Does that make sense? You're trying to see, what are you trying to see? So this is a 2 minus, oh my arrow's in the way, sorry. This is a 2 plus because our oxygen is a 2 minus. I know that because I can remember on my periodic table, the fluorine column is -1, oxygen column is -2. Okay, great. Okay, so I think you can do the rest of those. Let's see. So we're going to go over this, and then at the end, when we have work time, you can finish working on this. Let me go through, let's see. Okay, so let's look at some of the post-lab questions first. So in the post-lab questions, let's look at number 4. Post-lab question number 4 for part 1. It says, this is an exothermic reaction. We just talked about exothermic reactions in chapter 6. So somebody remind us what's happening with the energy. Good, energy is released. So that's something that you can say about an exothermic reaction. Okay, then it asks something about, you can conclude about the energy stored in the reactants compared to energy stored in the product. So we need to compare how much energy is in the product versus reactant. So to look at this would be helpful to look at one of our graphs, the exothermic graph. So let's draw that. When I'm drawing an exothermic graph, where do the levels go?
A little bit and down.
Products have to be lower, good, than the reactants. So this would be exothermic. So remember, this side is, do you remember what the title on this side is? Yeah, that's energy. And we just said this is the reactants, and this is our products. So what can you conclude about the energy in the reactants versus the products? Which one has more energy? Yes, in an exothermic reaction, reactants has more energy than the products. That's what it's asking you about, okay? So I think that graph helps explain that. Okay, then number 5 talks about other examples of exothermic reactions. So it gave you, which one did it say? It said the magnesium and oxygen. And then you're going to rewrite the balance equation. So first balance it, then you can write it here. How do you know if it's exothermic? Okay, if we're looking at the heat of reaction, we look at the negative sign. Good. In the lab, so you just told me before, energy is released in an exothermic reaction. What can we look at, or how do we know? It feels warm. Good. So if it feels warm, if it warms up, that's exothermic. So are there any of the reactions that you saw that felt warm? That's what this one's asking.
Oh, yeah, it was.
Okay, so look back through your notes, and you're going to balance those, and then you're going to write them here. Okay? So it also is asking about the one that they just talked about in number 4. So number 4, it told you that one was exothermic. So also write that one, okay? Okay, so that's number 5. All right. Let's go to the part 2 boxes now. We're gonna look at the chemical reactions in the boxes, part 2 boxes, okay? So we haven't talked about this yet, so let's go through this. So I started this and then I realized it tells you what to write. So that's pretty nice. Okay, so hopefully you have your description. Okay, this one didn't work very well for us, did it? I don't know. I think my chemical was mislabeled or something from the cupboard. But we are still going to write our formulas. So first, let's go to the balance equation. Okay, we're going to do, that's kind of hard to see. This is telling us what to write. So it says nickel 2 chloride. So what do we need to write in this box if it says nickel 2 chloride?
Nickel 2 plus C.
Okay, and we're going to write the whole formula out. This is going to be the balanced chemical formula, just like we did in chapter 5. So we have nickel, and then it has a 2 plus charge. So I'm going to write it up here. Let's do that. Nickel has a 2 plus charge. What's the charge on chlorine? Minus 1. Good, thank you. And so what would our formula be if we have a nickel 2 plus and a chlorine minus? We need 2 chlorines, perfect. So NiCl2 will be our formula for nickel 2 chloride. So we're going to write that formula, nickel 2 chloride, in our equation. Okay, so we have that done. Nickel 2 chloride, that's this, is added plus to sodium carbonate. So this one might be in your reactions from before, or we can look at what's the formula. We need to look at the formula again. So we have sodium. What's the charge on sodium? +1, thank you. And then we also need carbonate. Do you guys know carbonate from chapter 4? Carbon, oxygen. How many oxygens, do you know? CO3. And then do you remember the charge from chapter 4? Yeah, this one's 2 minus. Do you remember? So that's one of the polyatomic ions you had to remember for one of the topics. Okay. So then this is telling me that I need 2 sodiums for 1 carbonate to charge balance. Okay, I need 2 +1 charges for 1 2 minus charge. And then this will be my formula for sodium carbonate. Do you remember seeing that written on the container? Okay, so I have nickel chloride. I'm adding sodium carbonate to produce. So now we have our to produce arrow. We're getting nickel 2 carbonate. So do you think you can find the formula for that? What would we have nickel. It has a 2 plus charge. We have carbonate. What would our formula be? NiCO3, good. So Ni has a 2 plus charge. Carbonate has a 2 minus charge. We just need 1 of each to balance those. Or we could put the 2 down here and the 2 down here and then simplify. That would work too. Okay, and we get sodium chloride. Do you guys know the formula for that one? Yeah, that one's good. Hopefully we got that one down. Good. Cl, NaCl. Okay, so that's our balance. Oh, is it balanced? It's probably not balanced. That's our chemicals. Now we need to balance it. Thank you. Let's put a 2 on the sodium chloride. Okay, and that gets us 2 NAs, 2 NAs, 2 Cls, 2 Cls here, 1 nickel, 1 carbonate, 1 carbon, 3 oxygens. Okay, so that's balanced now. Okay, so that's what we're looking for, balance. Okay. let's look at this next, this box next. Formula of precipitate. So I don't think anyone, I'm not sure what happened, but something should have formed. We didn't see that. I'm not sure exactly what happened there.
Goo. It's pre-goo.
Was yours goo? Oh, the goo would be a solid. Okay, great. I'm glad yours worked. Okay, so we need to decide which of these is a solid. So we are going to use the chart. Let's see, do I have the chart or do you have the chart? I think, is it in here? I can't remember. Yeah, you have the chart. It's an instruction. Okay, let me hand out the instructions. Oh no, do you guys have the instructions? I think I do. Okay, if you have the instructions, pull out the instructions. If you don't have the instructions, yeah, I can get that one. I only have a few. Oh, I can pull it up. Ow! You have the instructions? I'm not sure. That was so good. Hey, I have some of these. So hang on for this. Make sure that you have Okay, we're using the same chart. All right, so hopefully you have, this is also, you can link if you use the electronic copy through Canvas. This is also on Canvas, okay? All right, so how this works is, this one has a key. So if it's green, it's soluble. So if it says yes, it's gonna dissolve, okay? So it's not gonna be a solid. So we have to decide, is nickel carbonate a solid or is sodium chloride a solid? So let's do this one, nickel carbonate. So we find nickel over here, nickel 2, and then we find carbonate. So it says no. So if it says no, that could be our solid, okay? So this one is going to be a solid. So for this lab, to get full points, you need to put the phase. Oops, there you go. This one is a solid, okay? These ones started dissolved. So what phase will they be? So this one is called the aqueous phase. So we're going to put AQ. That means it's dissolved in water. Dissolved in water.
We just kind of ignore it.
Sorry?
So there was water mixed in there. We just kind of ignore it.
Oh, so it's the solvent. So we don't write it in the equation. It's not really reacting. It's just there. Yeah, yep.
Kind of sits there.
Yes, yep. Okay, so let's also check this product. So see if you can figure out, is sodium chloride going to be a solid in water? Or is it gonna dissolve or is it gonna form a solid? So yeah, so sodium chloride will be soluble. So it will be aqueous. Good. Okay. Does that make sense, the process? So then, formula of precipitate. What's the precipitate in this reaction? NiCO3. Yep, so we're going to write that. NiCO3. Because it's a solid, we could put that. It's the solid. Okay. The next thing that we do is this complete ionic equation. So anything that's dissolved in water, anything that's in the aqueous phase, we're going to break into its ions because that's how it really is in the solution. It's not a solid, it's not together, it's in its ionic pieces. Okay? So what would our ion be for nickel? What's the ion form? Or I guess what's the charge on nickel? For this, it's 2. Nickel 2. It's this 2 plus. So Ni 2 plus. And then what do we say the chlorine charge was?
-1.
Good, -1. So, and how many of those are there?
2.
2. So as we go, let's balance. So there's 2 chlorines, and they have a minus charge. Okay. They're also aqueous, so we need to write that as we go. These are aqueous. Okay, this is going to take a lot of space, so I should probably have written smaller. Okay, then we have this one. This one is aqueous, so we have 2 sodium ions, 2 Na+. And what was our carbonate ion charge? This one's aqueous.
2-.
Good. So we just have one of those. CO3, 2-, that's aqueous. Okay. Oh, I'm going to put my arrow. I'm going to run out of space. I'm going to have to go out of my box. Okay, this one is a solid. So it's not in its ionic form. It's not broken into its ionic pieces. Okay, so it's has its ionic bond. Okay. So we just leave it just like this in our equation because it's a solid. Okay. It doesn't split apart in water. Not soluble. Okay. And then we decided sodium chloride breaks into its ions. So it's going to be, I'll put it here. We have 2 NAs. We said those were a plus charge. That's aqueous. And we have 2 chlorines. They're minus charge. They're also in the aqueous phase. They're dissolved in water. Okay, so that's our complete ionic equation. We have to do one more step. We have to do the net ionic equation. So net ionic equation is we look on the left and we look on the right, and if it shows up on the left and on the right, we can cancel it out. So is there anything on the left and on the right that we can cancel out? It doesn't really do anything. It's just floating around as an ion.
The 2Cl-.
Good, so 2Cl-. Those can drop out for this equation. Anything else? 2 Na+, good. So those are called spectator ions because they're just watching. They're not doing anything. Yep, good. And so then we're going to write everything else down. So we have this one. This is doing something. Nickel 2+ is combining with this carbonate ion. And then that is forming this solid. And then it's always good to make sure you balance it. So just check, make sure it looks balanced. It's still balanced. We got our phases on there. Okay, so that's how we do this problem. Okay, so I'm going to let you during work time finish that and work through that. If we need to come back during work time and work through some more, we can do that. Okay, but let's start there. I think you can figure out the rest. All right. Let's see. I think there was another question on here. So let's go to the post-lab questions for this section, part 2. So on the very back page of the data sheet, this post-lab questions. So this is something that you are going to have to look up. So it says, I think, does it say that in the instructions? I can't remember. Okay, yes. So in the instructions, after this table, if you go to this website, let's do that. So I'm going to go to Canvas, actually. Oops, not that one. So I can find the instructions on Canvas. This is lab 4. Lab 4 instructions. So on the very last page of the instructions, you can go to this website. Oops, is it? I have to click. Oh, there we go. Okay. And then, oh, I don't want to do that. Oh, thank you. Okay. There's not an X. Okay, I have to do that twice. All right, and then we're gonna look for our. Oh, thank you. Thanks. Okay, so what's our zip code? 84405. Okay, and what are we looking for? We're looking for a list of companies. Choose your water company, or you can choose one close to where you live. And the first question is asking you to list the name of the water company that you picked. Okay, and then look to see about exceeding guidelines, things that exceed guidelines and things that are others detected. The first question is going to ask us about nitrate. And we're going to look for, does nitrate exceed guidelines or is an other detected? Okay, so let's see. Should we do, we're in Washington Terrace. Should we try that? Okay, contaminate detected 11. Okay. Let's see, so we're looking for exceeds guidelines and then others detected. So we're looking for nitrate. And look at all of these. Nitrate, so this says exceeds guidelines. So that's nitrate fits in that one, exceeds guidelines.
About 5 times.
This one is Washington Terrace Water System. That's where the school would get our water from. Okay, so let's go back to, just for a second, let's go back to the questions. So this is asking, what's the name of the water company? And then which section did nitrate appear in? Exceeds. Okay. So then we talked briefly when we were doing the pre-lab about this flocking agent. So we talked about it's an ion to help settle out other ions. Okay, so let's look at this chart. The first question is asking, could a flocking agent be designed to precipitate nitrate? So look for nitrate. Where is nitrate? So is there anything that you could use to make nitrate be a solid? So these are all, so mine says yes is soluble. So is there anything, so Baden, you're saying no. Do we agree with that? Okay, so for this question, could a flocking agent be used to precipitate nitrate? Is there anything, so this one would be no. And then explain based on this chart, none of these ions will precipitate nitrate. Oops, I drew on that. Okay. Okay, so then we are going to try to pick one of these. Oh, wrong window. So you're going to pick something that's a cation.
25 times how much we should have in the person. And chloroform.
So look for something. It might be helpful to pick something that is on the chart. If we can't find it on this chart, there's another chart in the lab, so we can look for it there. So this website also has a chart. It's a little bit big, so sometimes it's hard to see, but okay, are there any of those that would be on here? We can also look at the other detectives, see if there's anything there. Barium, should we try barium? So let's go back here. So barium is on here. Barium. Oh. Oh, my thing's in the way. Okay, so barium is here. So is there anything that you could pick to make barium a solid, to precipitate out the barium, and then you could filter it out? What could you pick? Okay, so you're saying barium, you could pick carbonate, what else? Chromate and sulfate. So those ones. So this is like you're picking, so you don't have to pick barium, but some of us picked barium. And then this is asking which anions would you recommend? Okay. And then this is your possible flocking agent. So you're going to pick a chemical that has something and yes, for the flocking agent, just pick one. So like you decided that carbonate would precipitate barium. So is there another carbonate ion that you could dissolve, that you could add to your water that would precipitate barium? Okay, so potassium carbonate would be soluble. You could add it. That would precipitate the barium. Does that make sense? Okay. So go ahead and yes. Yep. Oops. There's lots of right answers for this. So you don't have to pick barium. You don't have to pick. Yes. So this one, you're picking something that precipitates barium. So or whatever. So maybe something else was in your iron, maybe or your water. Maybe copper was in your water. So pick something that precipitates the ion, and then pick something else that will dissolve. So like if I want to precipitate copper and I want to use hydroxide, maybe I want to add sodium hydroxide because that's soluble. And then the hydroxide will dissolve, then the hydroxide can react with the copper and make it a solid and precipitate. So my answer would be like sodium hydroxide.
Okay.
Does that make sense? Okay, yes, Rachel. Oh, yes. Yes. Yep, right, the correct formula. Good. Okay, great. Okay, so that is lab 4. We will take some time at the end for work time that you can work through that. So Monday, we're also going to do lab 5. So let's just talk for a minute about the pre-lab. Okay, for lab 5. Let me find the pre-lab. Modules, there you go. So I'm going to open the instructions in one tab, and we're going to do okay, I'm going to hand out the instructions. So I think this one is pretty straightforward, so I'm going to let you do the pre-lab. The answers are there. First, go over a step through and make sure to go mentally. Yes, good. You go. Okay, So lab 5 is you're finding unknowns. So we're going to start with some unknowns. And you're going to try to figure out what is present, okay? So you can either so part of this lab is that you have to come up with a procedure. What are you going to do? How are you going to figure out what's in your unknown? So you can do that on Monday when you come, or if you want to do it outside of class before you come, you can also do that, okay? So let's see. Let's look through quickly. I think that most of these you're going to be able to find. Okay, so like this one, if you're looking through for part 1, there's 2 parts, part 1, part 2. You cannot use chemicals in part 1, in part 2, okay? So looking through, what could be in your unknowns? So you have a materials list for part 1. So hopefully that's pretty straightforward. You will have, there's 7 items in the materials. Okay. Question 2 is asking the same thing, but you're just looking at part 2. What could be in the unknowns? So on part 2, they're solids, so they can't be the liquids in the material section. So watch out for that. So hopefully you can find that. Okay. Question 3 asks, when should you seek your instructor approval? Hopefully you can find that in the instructions. Let me click to the instructions. So remember, you're going to create a procedure for both, for part 1 and part 2. Once you have your procedure, you're going to come check with me and make sure that you can start. So that's when you're going to check with me. Before you start part 1, before you start part 2, I'm going to look at your procedure and make sure that it is reasonable. Okay? Yes. I'm going to put everything together and put it in the Bunsen burner. That's probably not a good idea.
That's a good idea.
Okay. Let's look at question 4 together. So if you have, how many things are in part 1? Okay, so if we combine 6 things with 6 other things, how many possibilities are there? Yeah, good. Possibly.
Oh, this is really fun math.
Okay, do you guys know what a spot plate is? So let's see if we can find that really fast. Spot plate, or I have some in the lab I can pull out. Spot plate. Okay, so this is a spot plate. Why would we use something like this?
So you can set up side-by-side comparisons and be really efficient.
Yeah, and be really efficient. For a spot plate, you just need a little bit of material. Yeah, and you can compare them side by side. That's great.
And it's a little bit fast.
Okay, yes, great. Okay, so that is what a spot plate is. Okay. You can probably find number 6. Okay, what about this one? I can check to see if my answer for what's in the vial is correct. So hopefully you can find that in the instructions. Let's look through. In step 9 it says,
Okay.
your instructor will only tell you if you got it right. So in part 2, what's in the vial?
Did I get it right?
I can tell you if you're right or not. Okay. All right. Okay, so that's the pre-lab for lab 5. So be thinking about, so you're going to have 6 things in part 1, 6 solutions, and 4 solids in part 2. So they're 2 separate experiments. If we need to take another day, we can. So be thinking about how are you going to test them? What are you going to do to see what's in the 6 vials, or how are you going to know what are in the 4 samples? Okay, and we can talk more about that on Monday, but start thinking about that. Okay, so now we have 35 minutes left. Let's go to some topics in chapter 6. Let me pull over our 7. We just did chapter 6. Yes. Keep this class, and I'll turn off some more for the next class. I can't remember who made this. So that's the only one things that you have to share or you can hang on to that. So it would be hard to tell what it is if you use them all. And it's probably the more multiple products that you have to separate them. So it would get messy. So also waste, the more you can keep the waste separated, the cheaper it is. Okay, this section is on pressure and ideal gas law. So the first thing we're going to do is another conversion problem. So do you remember? Oh, sorry. Yes. That's about part 1.
Yeah.
Yes. Okay, so do you remember last time we had a conversion problem converting units of energy? Do you remember doing that? So now we're going to convert units using pressures. So we need to figure out what unit we should use. So let me pull this over just really quick. This is in the Alex data. And again, you can use that on the test. But because you know that you're going to need this, I would probably write this on my note card. I'm going to write these conversion factors down. If I can find my Alex data. Let me turn this off. So under, conversion factors for non-SI units. So the fourth one down, 1, 2, 3, 4. This has units for pressure, so atmospheres, and then we can convert atmospheres into all of these. So for this problem specifically, we are going to look at, so we're going to convert atmosphere. So for 1 atmosphere, that is the same as, this problem we're going to use torr. Oops. What is it equal to? It's equal to 760 torr. And 1 atmosphere is the same as 760 millimeters of mercury. Okay. And I think these are the only ones that come up on this topic, but if I needed to convert into other units, those are also here. Okay, we might for the other topics, I can't remember. So what do you notice about these two, torr and millimeters of mercury? They're the same. So what does that tell you about if I'm trying to, they're the same, right? So if I have 1 torr, what is that in millimeters of mercury? 1. Okay, so that's going to also help us. So these are the 3 conversion factors that I think are going to help us the most on this topic. But So I would write this on my note card, but you could also find it in the Alex data. Okay. All right, so let's go back to our question. So this one says the vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury. So that's my given value. I'm going to write that down. 23.8 millimeters of mercury. Okay, and I need to convert that into atmosphere and torr, and I can just look at this box to tell me. We need to see how many millimeters of mercury is in atmospheres, what is this in torr? So which one would be the easiest one to do? Torr. And what should it be? The same. Great. And then let's practice. How many sig figs does this have?
3.
Yep, so how many does this need?
3.
Also 3. Great, so let's put that in, 23.8. So that one's done. So now we just need to convert this into, we're trying to get it to atmosphere. So my answer has atmospheres. So in my conversion, where does atmosphere need to go? Top. Good. So 1 atmosphere. And what should go on the bottom? You got it. 760. Oops, that's right. The right number. Millimeters of mercury. That cancels out. We get atmospheres. Okay, I'm going to use my Alex calculator. So I have this number, 23.8. I'm going to divide by 760. Okay, how many sig figs did I need? 3. Okay, so I can just put, so I'm going to put 0.0 and then 3.3. We could also do that. So this would be acceptable, or we could put it in scientific notation and keep 3 that way. So either of those should be acceptable. Okay. Questions on this one? Should we do another one?
Yes.
Okay, let's do another one. Sorry? Yes, you want a note card now? Okay, yes.
So the degrees Celsius
No. No, not for this problem, no. The vapor pressure does change based on the temperature. But
Just throwing that out there to be accurate.
You use the conversion.
but I like to review all of the topics and then write down.
okay, you wanted to try another one? Okay. Yes, let's try again. Oh, I thought I went. Okay.
What's the conversion? What atmosphere?
Oh, 1 atmosphere is 760 torr. Okay, so this one, we have, our value is, the vapor pressure of ethanol at 25 degrees is 0.0773 atmospheres. And we need to convert that into millimeters of mercury and torr. So we'll just do millimeters of mercury first because that's on the top. Let me erase this so it fits. Okay, I'm looking for millimeters of mercury. I kind of squished that on there. What should our conversion factor be to convert atmosphere to millimeters of mercury?
760 millimeters.
Okay, good. Millimeters of mercury for every 1 atmosphere. And that just comes straight from our conversion. We know that there's 760 millimeters of mercury for 1 atmosphere. We're doing okay there? Okay, so then atmospheres cancel out. We end up with millimeters of mercury. And we just need to type that in. Let's see. Alex calculator. 0.0773 divided by, oh, not divided by, times by 760. Okay, let's go back to our value. How many sig figs does this have?
3.
3. Good. So this has 3, so our answer should have 3. So what should we round this one to? Okay, 58.7. All right, what are we going to do to get to torr?
It's the exact same thing.
It's the same. Good. So if we have it in torr, then we can use that same number for millimeters of mercury. That's the same. 58.7. Okay, better check it. Okay, questions on that one? Do you feel like you could do that? Okay. All right, let's see. What's the next topic? Okay, we're going to just look at a few notes really quick. Oh, my notes are on the other screen. Okay, we're going to start here. Okay, so we're not going to start on this problem, but we're going to start with this equation. So this is called the ideal gas law. Have you heard of that? Okay. Alex calls this the ideal equation of state, but this is our ideal gas law. Okay. And this is what we stand for. P is for pressure. We have lots of units for pressure, so we need to make sure that our units are matching. Okay. V is volume. We should make sure that it's in liters. So we might have to convert to make sure that our units are in liters. N is the number of moles. R is the universal gas constant, and this is the universal gas constant that we want to use. This isn't Alex. We can always look this up. This is always the same. It's a constant. We're going to use this version. Okay, so watch out for this one. This one also shows up in Alex. We want to use this version. Okay, and then temperature for the ideal gas law. When we're using the ideal gas law, we want to use temperature in Kelvin. Okay, this gas constant is going to tell us the unit. So if you can't remember, look at the gas constant. Liters is our volume. So our volume has to be in liters. Our pressure has to be in atmosphere. Our number of moles needs to be in moles. Okay, sometimes we get the number of grams and we have to convert to moles. And we need to make sure our temperature is in Kelvin when we're using the ideal gas law and we're using this gas constant. So I've linked a PhET simulation in our slides, and you can kind of play around. So this is a relationship. This is telling us if we change the pressure of the gas, what's going to happen to the other parts of the gas. If I change the temperature of the gas, what's going to happen? Okay, and so we have this mathematical relationship, and that's going to help us know what happens to the pressure if we change the temperature. What happens to the volume if we change the pressure? Okay, and if you want to play around with this simulation, you can kind of look at that. Okay, so we are going to look at a version of the ideal gas law. Oh, first, the ideal gas law is for ideal gases. So when we're talking about an ideal gas, we're talking about something that doesn't interact with itself. So it's like they bounce off each other. They're not sticking together at all. Okay, the molecules have no interaction with each other. And things like noble gases are going to be most like an ideal gas, or like nitrogen and hydrogen. Things that are small and they don't have a lot of electrons are going to be the most non-interacting. Yeah, they won't interact with each other. Okay. So the first type of, so this is related to the ideal gas law. This is when we take the ideal gas law and we say that the number of moles is not changing and the temperature is not changing. If the number of moles and the temperature are not changing, then we have Boyle's law. So we have this relationship, P1V1 equals P2V2. So this is kind of explaining what's going on. If you have, this is when I think of this problem, I think it's called the piston problem, because when it comes up in Alex, it always has a piston. So if you pull up, so imagine you're pulling up, the volume is increasing and the pressure is decreasing. So think of it, I didn't bring one out, but if you think of a syringe and you put your thumb on the end of the syringe and you pull it, what happens to your thumb? It like sucks your thumb in, right? It's creating a vacuum. Your pressure is decreasing. If you push, so imagine you're pushing a syringe onto your thumb, what's happening? Yeah, you're increasing the pressure on your thumb, okay? So that's what this law is, okay? So it's pretty intuitive, but it does come from the ideal gas law. So let's do some examples of this, and then we'll probably take some time to do work time. So let's go to Alex. Let's go to the ideal gas law. Let's see if we can find it. Or not ideal, we're looking for Boyle's law. Understanding Boyle's law. So again, this one is the piston problem, okay? So imagine you're either pulling out a syringe or pushing in a syringe. Okay, let me put my... Let's flip over this. Oh, that's stuff in the back too. Okay, so if we're doing the piston problem, that's Boyle's law, the person who found this relationship. And our equation is P1V1 is equal to P2V2. And if you're feeling ambitious, you can say, well, the N is constant, T is constant, R is a constant, it's always a constant. So during Boyle's law, we don't change the number of moles, we don't change the temperature, R is always the same, and you can prove that this is true. So if you wanted to do that with the math, you can do that. Okay, so what we need to do is we need to read the problem, see what we have, and see what we're trying to find. So what I like to do is I have my equation, and then I like to write out my P1V1, P2V2. So write out those values. So let's read the question. It says, a cylinder is filled with 10 liters of gas. So what's that number? Volume, and that's our initial volume, volume 1, 10 liters. Okay, how many sig figs does that have? Good. So make sure you're checking that as we go. Okay, the initial pressure, so what's that? Initial pressure is 251 kilopascals. So that's P1, right? How many sig figs?
3.
Also 3, great. Okay, and then the piston is now pushed down. So imagine you're pushing that syringe, compressing the gas until the gas has a final volume of 5.6 liters. So where does that go? Yeah, V2 is good, 5.60 liters. Okay, so what are we looking for? We're looking for P2. So then we just set this up. We have P1. P1 is, I'm going to put it right here. P1 is 251. Oh, it's not going to fit. I'm going to have to write smaller. 251 kilopascals. Still not going to fit. I'm going to have to come down here. So P1 V1 equals P2 V2. I have P1 is 251 kilopascals. Volume is 10 liters. P2, we don't know P2, that's what we're looking for. And V2 was 5.60 liters. Okay, so how are we going to solve for P2?
Multiply the other end.
Yeah, multiply these two and divide by this other one. Great, 5.60 liters. Okay, so these cancel out. We'll get P2. So look at our units over here. What's happening? They should be canceling out. So we got liters on the bottom, liters on the top. We end up with kilopascals. Let's look at our answer box. It's also in kilopascals, so we don't have to do any unit conversions for this problem. So that's nice. Okay, so let's do that on, I'm gonna do that on the calculator. Oops, I don't have enough space over here. Let's calculator up here. Okay, so we've got 251 times by 10 divided by 5.6. Okay, and then how many significant digits should we have? 3, good. So remember, this is not going to tell you that on the test. You have to practice remembering. So 448 decimal.
It's not an iteration. It's not an iteration of counting.
Yes. Okay. We should round. Yes. Okay. All right. Do you want to do another one of those or have some work time? Work time? Okay. All right. Okay. Work for, we got 15 minutes left.
So